Proof of that, I gave you the idea in class. If you go back in your notes, hopefully you wrote that down. I did go over the idea of the proof of Fermat's theorem. It's not too hard, though it's a little tricky. The other named theorem that I've given a name to that the book does not is the uniform continuity theorem. But continuing in chapter 4, going backwards, I guess some named theorems include the derivative rules, but I will not have you state the derivative rules, but you might need to use them. Product rule, quotient rule, chain rule. I won't have you state those, but you might need to use them, so of course you should know them. And not just to take derivatives of particular functions, but to also be able to think about the abstract formula. For example, for the chain rule, you could write the abstract formula like this. The derivative of f of g of x is f prime of g of x times g prime of x. And sometimes I think I've given problems, like you'll find in the calc book actually, where you've got a table of values for f of g, f prime and g prime, and you've got to use, no formulas, you've got to use the abstract form of the chain rule to find a derivative. If you call this function h of x, maybe I might say find h prime of 4 when you know facts about values of f, g, f prime, and g prime at different values of x. You'll find those kinds of problems in calc books too. Will you need to prove any of these rules? The product rule is a possibility. It does involve a trick. So you should study it so you remember the trick. And once you see the trick, then it's just properties of limits and your hypotheses about f and g. You might have to calculate a derivative with the limit definition. So you had some homework problems like that. We did a few examples in class. There were those two ways of doing it, two slightly different limit calculations that produce the same result. Probably I'd say you can use either one, whichever you prefer. Chapter 3. You should know the definition of a variation, the variation of a function, and what it means for a function to have bounded variation. By the way, it actually would make more sense to me to switch around the definitions of oscillation and variation. I think this idea from chapter 3 should be called the oscillation, because it's it's related to how much goes up and down. According to the book, it's called the variation. And I think the oscillation, being the max minus the min, effectively, should be called the variation. But we don't live in that world. We go with what the book does. And I think the rest of the stuff in here is maybe fodder for true-false questions. Monotone functions have one-sided limits. They have at most a countable number of discontinuities. Countable includes finite and countably infinite, but it can't be uncountable. Section 3.4, there's the definition of uniform continuity and the uniform continuity theorem as things you should be able to state. And I think on old tests and possibly on yours, I certainly have put problems where I say prove this function is uniformly continuous, or even prove it's not uniformly continuous on a certain interval from the definition. There's a couple of Cauchy criteria that I've skipped essentially. Cauchy criterion for limits on page 113. There's also a Cauchy criterion for Riemann integrability in section 5.2. I've skipped those, they won't be on the test. Going back into section 3.3, we did not talk at all about what it means to be locally bounded, so I think that will not be on the test. But we did talk about the intermediate value property, the definition. Yeah, I think you should be able to state the intermediate value property, or at least be able to identify it in true, false, and multiple choice questions. The theorem that comes right after that, it technically is good to know, but I'm not going to put it on the test. I'm talking about theorem 3.24, page 105, will not be on the test. Facts about continuity include that the algebraic combinations of continuous functions are continuous sums, differences, products, quotients, as long as you're not dividing by 0. Also compositions, f of g of x, of continuous functions are continuous. And inverse functions of continuous and strictly monotone functions are continuous. Strictly monotone. It's got to be strictly monotone to be invertible in the first place. Then there's the big theorems about continuity, the EVT and the IVT. As I said when we were talking about those, you should certainly know their statements and their proofs. I think the most common thing I've done on old exams is prove the second paragraph in the extreme value theorem proof, except possibly for imps instead of sups. That's probably the most common thing that I've done. So it's a two-part proof for the extreme value theorem. First, prove the function is bounded on the interval. You should study that. It's a possibility. I'm not ruling it out. It does require the Bolzano-Weierstrass theorem that any bounded sequence has a convergent subsequence. And in fact, if the bounded sequence is in a particularly closed interval, it has a subsequence that converges to a point in that closed interval that's necessary for the first paragraph to show the function is bounded. You argue by contradiction, assume to the contrary it's unbounded. And then the second part, the book proves that there is a point D such that f of D is the maximum value of the function on the closed interval, the continuous function. And they use a sup, completeness axiom comes in there, and the Bolzano-Weierstrass theorem is used in the second paragraph as well. What I've most commonly done in exams is prove that a function attains its inf, a continuous function on the closed interval. And so you need to use the inf, which means use the completeness axiom. And you don't need to say, you don't need to prove that infs exist from the completeness axiom. You can just assume by the completeness axiom that infs of bounded sets exist as real numbers, and you don't need to, even though that's not the statement of the completeness axiom, it's stated in terms of sups. And then the Bolzano-Weierstrass theorem is used again.
Where is this beta minus 1 over n come from?
That's a little trick. That's a trick they use to help them finish the proof. So you would do, if alpha was the inf, you'd consider alpha plus 1 over n. The intermediate value theorem proof is a possibility as well, though that's a little tricky. Maybe I'd give you a little bit of guidance. Maybe I'd tell you what S is. And I'd say to let C equal a sup, and you finish it from there or something. .1 is the definition of a limit and properties of limits. We are about out of time. That includes the squeeze theorem. I think I've almost always put a problem on the test where you've got to use the definition of a limit for probably a quadratic is the most likely. So it's a lot, when you think about it. Chapters 3, 4, and sections 5.1 and 5.2. There's a lot to study. See you on Wednesday. We will start early again. What did I say, 7:20? Was that kind of the first exam? I think so. Plan 7:20. See you.